So my main aim of this presentation is to give some brief idea about some new areas in functional analysis which we can do research, and we can explore the existing ideas in classical normed spaces and Banach spaces to this new structure. And some of the, I know that majority of the students attending here are MSc students, so they can think for a MSc project also in these areas. Nowadays, many students are struggling to identify topics to do project. So they can, those who are interested in functional analysis, they can choose one such area as probabilistic normed spaces. So my outline of this presentations are, first I want to tell some of the ingredients for to explain what is probabilistic metric spaces and probabilistic normed spaces. So I will begin with the concept of distribution functions and some of its properties, and how can we metrize the collection of distribution functions. And later we will go to the concept of probabilistic metric spaces and some of the classical theorems in our uh, usual metric spaces are proved in probabilistic metric spaces, that will be highlighted there. And throughout this presentation, I am not going through any of the proof part. And still, it is a new idea to all the people. The concepts itself will be somewhat difficult to understand also. Then I will move on to the concept of probabilistic normed spaces. Then I will just explain how a topology can be constructed in a probabilistic normed spaces. And what about the uniform continuity of a probabilistic norm? And next, I will discuss about whether all probabilistic norm spaces are topologic vector spaces or not. If not, under what circumstances it will be a topological vector spaces. And next, finally, I will discuss some of the results in finite dimensional PN spaces. And after that, I will just give recent developments in probabilistic norm spaces. So to start with that, those students and other participants, those who have studied about the probability theory in your master program, you might have heard about the definition of distribution function. So distribution function is nothing but a function going from extended real line to the closed interval 0, 1, satisfying the properties. At minus infinite, the functional value should be 0, and at infinite, it should be 1. And the function should be a non-decreasing function, and f should be left continuous on its domain. So if these three conditions are satisfying, such functions from the extended real line to 0, 1 is a distribution function. So throughout here, we have to take some of the particular distribution functions, namely epsilon a of x, which is defined as 0 from minus infinity to a, including a, and 1 if it is from a to infinite. It is like it's just nothing but a step function. And epsilon infinite of x is defined as 0 from minus infinity to plus infinite, excluding plus infinite. At plus infinite, we are defining it as 1. And I'm denoting the set of all distribution functions by capital delta. And from that set of all distribution function, I am taking a subclass that is nothing but delta plus those distribution functions satisfying the condition that f of 0 equal to 0. So the next question comes in our mind is, can we define an order on this delta and delta plus? Yes, we can. If we are able to define an order on that one, then we can think about whether it is a partial order on that one. Then we can look for the maximal and minimal elements of that set based on the given order. So we can define a partial order on delta and delta plus by our point-wise partial ordering. You take any two f and g from delta and delta plus, f less than or equal to g if and only if f of x less than or equal to g of x for every x in the domain. So it is already proved that epsilon infinite is nothing but the minimal element for both delta and delta plus based on this order. And epsilon minus infinite is the maximal element for the whole distribution functions collection, whereas the maximal element of this that subclass delta plus is nothing but epsilon 0. So the now we constructed a partially ordered set using this collection of the distribution functions. So next question is, how can we metrize this distributions functions collection? So to define a metric, there are the different metrics defined on the distribution functions collection. So we are choosing well accepted one definition only here. To define that one, we need a condition. So you take any two distribution function f and g and take an element h belongs to open close to 0, 1. I'm denoting a condition with this symbol, that is f g colon h. It denotes this condition, that is g of x should lie between f of x minus h and f of x plus h for all x belongs to open interval minus 1 by h, 1 by h. With respect to this condition, we are going to define a metric on the set of all distribution functions collection. So that metric was introduced by the mathematician Sibley. So I'm going to show how they are defining that metric on this collection of distribution functions. So we are denoting that Sibley metric by d suffix s. Take any two functions f and g from delta. ds of fg is nothing but the infimum of all h belongs to open closed interval 0, 1, such that this two condition holds, fgh and gfh. fgh I have just shown in the previous slide. What is that condition? That is f of x minus h less than or equal to g of x less than or equal to f of x plus h plus h. In the similar way, this condition also should satisfy together. And one can easily see that this set inside this infimum, it is non-empty because fg1 and gf1 will hold. So it is non-empty. And it is proved that this Sibley metric between f and g will be less than or equal to 1. And this function ds is going from delta cross delta to r plus. It's a metric on delta. And so that the set of all distribution functions delta together with this ds is a metric space. And this metric space is complete as well as compact. And next, the topology of the metric ds and the topology of the weak convergence will coincide here. In the set of all distribution collections, the topology of the metric ds and the topology of the weak convergence coincide. What does it mean? That is, if you take a sequence fn of distribution functions which converges weakly to a distribution function f, if and only if, what we can tell, the sequence fn of x converges to f of x at each continuity point of f. And it is proved that because of one pop-up line, that last line is not visible here. If fn converges to f weakly, then if and only if the Sibley metric between fn and f will tend to 0, because that result is quite often used in the previous many results. So this is the way we are defining the metric on a collection of distribution functions. And with respect to that one, we can tell some of the basic properties of the distribution functions collection. So I told you that my main aim is to define the probabilistic metric space and probabilistic noun space. So to define that one, we need some more concepts here. Next one is, what do you mean by a triangle function? So triangle function, it is nothing but a binary operation on delta plus. So delta plus, you know that when those distribution functions such that f of 0 equal to 0. So tau is a binary operation on delta plus with certain conditions. That is, tau should be commutative, tau should be associative, and tau is non-decreasing in each place. Non-decreasing in each place means f less than or equal to g, then tau of fh less than or equal to tau of gh, and tau has epsilon naught as the identity. That means tau of f comma epsilon naught should be equal to f. So the next idea I'm going to use is triangular norm. In short, it is known as T norm. So triangular norm is again a binary operation. In the triangle function, you have seen that triangle function is a function, or sorry, it's a binary operation on delta plus. Here it is a binary operation on closed interval 0, 1, satisfying the condition tau of xy is equal to tau of yx, and that means it is commutative. And the second condition stands for it is tau is associative and it is non-decreasing, and here the identity element should be 1. So we can discuss about the continuity of triangle function. Continuity of triangle function is nothing but the continuity with respect to the topology of weak convergence in delta plus. And throughout this section, we have to see some of the typical continuous triangle functions. One such function is the convolution, and another functions are shown here. That is tau suffix capital T of f comma g. That is, this capital T is nothing but the triangle function. Tau suffix capital T of f comma g of x is equal to supremum of tau of f of s comma g of t. Supremum is taken over all the elements s and t such that s plus t is equal to x. And tau suffix tau star is also another t norm that I will tell you in the next slide how this tau star can be constructed. Since I want to tell these two typical continuous triangle functions together, that's why I have shown here tau suffix t star of f comma g is equal to infimum of t star of f of s comma g of t. Here again, infimum is taken over all the s plus t is equal to s. So here t star means t star is a continuous function and it is called the t conorm. How the t conorm can be defined is t conorm is also a binary operation on closed interval 0, 1, which is related to the corresponding t norm capital T. How can we define that t conorm of any triangular norm, that or t norm is nothing but t star of xy is nothing equal to 1 minus t of 1 minus x 1 minus y. Here capital T is nothing but the given t norm. If you want to define a t conorm, first of all you should have a t norm with you. With respect to the t norm, you can define a t conorm in this way. This is the definition of defining what a t conorm using a t norm. And I will show some of the examples of t norms and t conorms. If I take capital T as capital M, that is m of xy is equal to maximum of x and y, it will satisfy all the conditions of a t norm. So this is a simple example for a t norm. This is called the maximum t norm. And the corresponding t conorm is nothing but m star of xy is nothing but minimum of x comma y. And there are some more t norms and t conorms. That is pi of xy is equal to xy. It is a t norm. And the corresponding t conorm is pi star of xy is equal to x plus y minus xy. This is called the product t norm, and this is called the probabilistic sum t conorm. So the next type of t norm we can define is w of xy is equal to maximum of x plus y minus 1 comma 0, and w star of xy is equal to minimum of x plus y equal to 1. This w is nothing but a t norm, and w star is the corresponding t conorm. And another one, d of xy is equal to minimum of x and y if maximum of x and y is 1, because the t norm is defined in what closed interval 0 1. It's a binary operation on closed interval 0 1 and 0 elsewhere, and this is called the drastic t norm. And its corresponding t conorm, that is d star of xy is equal to maximum of xy if minimum of xy is equal to 0 and 1 otherwise. This is called the strongest t conorm. Among all the t conorm, this is called the strongest t conorm. And you can take the collection of all t norms, and you can make it into a partially ordered set with the help of the pointwise partial ordering. Then one can easily get that it is a proved result. The t norm w is less than or equal to pi less than or equal to capital M. And from this one we can conclude that capital M is the maximal t norm, and since minimum of xy is less than or equal to maximum of xy for all x and y in 0 comma 1, one can conclude that the t norm of x comma y will be always less than or equal to t star of xy for every t norm t and t conorm t star. And if you take the set of all triangle functions, the set of all triangle functions is a partially ordered set with respect to the partial ordering. If you take tau1 and tau2 are two triangle functions, tau1 and tau2 are related if tau1 of f comma g less than or equal to tau2 of f comma g for all f and g from the domain collection of distribution functions. So what we can tell is every continuous t norm t and continuous t conorm t star will satisfy the condition that tau suffix t is less than or equal to tau suffix t star. I have already explained this. What is tau suffix t? Tau suffix t is the t norm corresponding to that supremum norm, and t star is nothing but the t norm corresponding to that infimum norm. So another important concept we need is how can we tell that a t norm is Archimedean? If you want to talk about t norm is Archimedean, first you have to look for its t conorm. T conorm is nothing but denoted by tau star. Its t conorm admits no idempotence other than epsilon 0 and epsilon infinite. If that condition holds, then we can tell that the given t norm is Archimedean. This is one of the important concept required later to establish the answer of one of the important question I told in the outline. So now I will come to the one of the main concepts I wanted to discuss here, that is probabilistic metric spaces. This probabilistic metric spaces was introduced by the famous statistician as well as a mathematician Carl Menger in 1942. This Carl Menger is the student of Hahn. You all heard about Hahn-Banach theorem. In that, it is done by two mathematicians, that is Hahn and Banach. So he is the PhD student of Hahn, and he introduced the idea of statistical metric. What he did is, instead of considering the number for the distance between P and Q, from on a non-empty set, he wanted to map the d of pq to a distribution function. So what he did is, you take any t belongs to open closed 0 infinite, then f suffix pq of t, which is nothing but the probability that the distance between p and q is smaller than t. Instead of taking to a real number, he is mapping it to a distribution function. And distribution function, you know that it is a mapping from the extended real line to 0, 1. So finally, this f suffix pq of t will be a value between 0 and 1. So now I will formally tell what is the definition of probabilistic metric spaces proposed by Carl Menger. So for that one, you take a non-empty set capital S, you take a function f, which is from S cross S to delta plus, which is defined by f of pq equal to, we are denoting that one. What is the notation we are using here is f of p comma q is equal to f suffix pq. For our convenience, we are writing f suffix pq. And tau is a triangle function. And we can tell that this f is a probabilistic metric on the non-empty set S if the following condition holds. For all PQ are in S, first condition should satisfy is f suffix pp should be equal to epsilon 0. You know that epsilon 0 is one of the particular distribution function we have considered in the beginning. And if you take the element as p and q are same, then what should happen is f pp of t should be equal to epsilon naught of t. That is the meaning of this one. F suffix p comma p equal to epsilon naught means f suffix p comma p at t should be equal to epsilon naught of t. And if p and q are different, f pq should be different from epsilon naught. And the third one, f suffix pq equal to f suffix qp. It is somewhat similar to our symmetry property in normal metric definition. And the fourth condition is f suffix pr should be greater than or equal to tau of f of pq comma f of qr. You know that tau is a triangle function. Triangle function is nothing but a binary operation. So with respect to that binary operation, this final condition should satisfy. That is f suffix p comma r should be greater than or equal to tau of f suffix pq comma f suffix qr. If these four conditions are satisfying for the given function, then we call this f as a probabilistic metric on S, and the triplet S, f, and tau is a probabilistic metric space. I will show one example here. I am not going to verify it here. You take a classical metric space MD, then define f of pq. That means f suffix p comma q is nothing but epsilon suffix distance between p and q. Epsilon suffix distance between p and q for all p and q in M. And you take the triangle function tau t as that supremum definition, then you can verify all the conditions of this probabilistic metric for this this setting. Then you can tell that the triplet M, F, and tau is a probabilistic metric space. There are some interesting results done in this probabilistic metric spaces. Almost all the results done in probabilistic metric spaces as well as probabilistic norm spaces are the analogous results from our classical metric spaces and norm spaces, because this probabilistic metric spaces and probabilistic norm spaces are a new algebraic structure. So in that new algebraic settings, whether our classical results from the metric spaces and the norm spaces will work is the biggest challenge. In case if it is not working, under what condition it will work. That is the main challenge in front of us. For that one, we need some definitions here. That first definition I want to tell is probabilistic diameter. For that, you take a subset of a probabilistic metric space S. A is a subset of S. Then define a mapping D suffix A, which is going from the extended real line to real line R, defined by at infinite dA of infinite is 1, and for all x greater than 0, uh, dA of x is equal to, you take the infimum of all fp of x corresponding to all p and q from A, then you take its supremum based on t less than x. So that is nothing but dA of x. This dA of x is called as the probabilistic diameter of a subset of a metric space. So next, when we can tell a set is a subset of a metric, probabilistic metric space is said to be probabilistic bounded. If that supreme of that probabilistic diameter is 1 for all x greater than 0, then we can tell that A is probabilistic bounded. If this supremum lies between 0 and 1, strictly lies between 0 and 1, then we will call it as probabilistic semi-bounded. And if this supremum, sorry, not supremum, if the diameter itself is 0, then we will call it as probabilistic unbounded. So these are the terminologies we need to look for some of the basic results established in this concept. So next, the strong topology defined on this probabilistic metric space, how it is defined is given here. It is introduced by a strong neighborhood system. We have to take a strong neighborhood system, capital N, which is equal to the union of NP of T. Union is taken over P belongs to S and T greater than 0. How that NP of T is defined? NP of T is nothing but set of all Q in S such that the probabilistic metric between P and Q at T should be greater than 1 minus T. So in how can we tell in another way? Based on the Sibley metric, how can we tell it? It is equal to set of all Q in S such that the Sibley metric between F suffix PQ and the epsilon naught should be less than T. This NP of T is nothing but the strong neighborhoods, and this N equal to collection N equal to union that NP of T, that is the strong neighborhood system here. So next, you take as probabilistic metric space S, F, and tau. Take any non-empty set A. If the family of sets V alpha corresponding to alpha from the index set I, such that A is contained in the union of V alpha, then we call this collection V alpha, alpha in I is a cover of A. All these similar definitions you have studied in your classical metric spaces. So next, what do you mean by a non-empty subset of a metric space is said to be probabilistic totally bounded? For every epsilon greater than 0, capital A can be covered by finitely many neighborhoods NP of epsilon, where P belongs to A. Then we can tell that A is probabilistic totally bounded. Equivalently, how can you tell this same concept? For each epsilon greater than 0 and P in A, if there exist elements P1, P2, etc., Pn in A, such that the probabilistic metric between Pi and P at the positive number epsilon should be 1 for all I belongs to set 1, 2, 3, etc. n. Then we can tell that this is a non-empty subset. A is a probabilistic totally bounded set of what? The metric space S. So immediately one result is established in the probabilistic metric space, every probabilistic totally bounded set is probabilistic bounded. If you take any probabilistic totally bounded set in a probabilistic metric space, then it will be what? Probabilistic bounded. So it's a well-known theorem in our classical metric space as Cantor's intersection theorem. So the analogous of this Cantor's intersection theorem is established in probabilistic metric spaces, which states that you take a probabilistic metric space capital S, and tau is a continuous triangle function. Then this metric space is complete if and only if every nested sequence Sn of non-empty closed subsets of the metric space S, such that the diameter, probabilistic diameter corresponding to each element in the nested sequence will converge to what? Epsilon 0 as n tends to infinite. Then the intersection of that nested sequence consists of exactly one point. That means it is non-empty. So this is the analogous of what Cantor's intersection theorem in probabilistic metric spaces. So next, the analogous of this Bayes' theorem in probabilistic metric spaces, which states that if you take a complete probabilistic metric space under a triangle function tau, take a sequence of dense open subsets of S as collection Gn, then intersection Gn is non-empty. That means, in fact, we can tell that it is dense in capital S. So this is the analogous result of Bayes' theorem from our classical metric space to probabilistic metric space. The proof is very lengthy, so that's why I skip the proofs and all. So to tell the next result, I want to talk about how this convergence and the concept of Cauchy sequence, which is defined in the probabilistic metric space. You take a probabilistic metric space capital S and take a sequence Pn from S, which converges to a point P in S, when we can tell the definitions are almost similar to our normal settings. For each epsilon greater than 0 and lambda belongs to 0, 1, there exists a positive integer m, such that after that stage m, what should happen? The probabilistic metric between Pn and P at epsilon is here. There is a typo. It's greater than, two symbols came here, greater than 1 minus lambda. Or in another way, we can tell that the Sibley metric between P and P and epsilon naught should be less than lambda. Next, you take a sequence Pn in S. It is said to be Cauchy. It is said to be a Cauchy sequence. If for each epsilon greater than 0 and lambda belongs to 0, 1, there exists a positive integer m, such that, there exists a positive integer k. It should be k, such that the distance, the probabilistic metric between Pn and Pm at epsilon should be, again, it should be greater than 1 minus lambda for all n greater than m greater than or equal to k. This should be k. There is a typo came here. And the probabilistic metric space S is said to be complete if every Cauchy sequence is convergent to a point in S. So with respect to these definitions and the earlier concepts, the following well-known results from our metric space to probabilistic metric space is established. You take any probabilistic metric space capital S with a continuous triangle function tau. If E is a subset of S, then the following conditions are equivalent. The first one says that E is complete and probabilistic totally bounded. The second result is nothing but the Bolzano-Weierstrass property. Every sequence in E has a subsequence converges to a point of E. And the third one, the Hain-Borel property. If you take a cover of that subset E of open sets, then there is a finite set F of that index set A such that that subcollection V alpha such that alpha belongs to F covers E. So it is proved that these three conditions are equivalent. So now I will come to the idea of what do you mean by probabilistic normed space. So to define a probabilistic normed space, first we need a linear space capital V. And to define a probabilistic metric space, we took a non-empty set and one triangle function. Here we need two triangle functions, tau and tau star, or continuous triangle functions. And I am taking a mapping nu. Nu is a mapping from capital V to delta plus. Delta plus means set of all distribution functions such that f of 0 equal to 0. Then this mapping nu should satisfy certain conditions. Then we can tell that this mapping nu is called a probabilistic norm on V, and then this quadruple V nu tau star is called a probabilistic norm space. The first condition should satisfy is nu suffix p. Nu suffix p means it will be a element in delta plus, but delta plus is from extended real line to 0, 1. So actual meaning of this nu p equal to epsilon 0. This is a function. This is a function. These two are equal means at t belongs to where my extended real line minus infinite infinite. So nu suffix p of t should be equal to epsilon t if and only if p equal to theta. That theta is nothing but what? The null vector in the linear space V. The second one is nu suffix, for every p in V, nu suffix minus p should be equal to nu suffix p. And the third one, it is somewhat similar to our triangle inequality. Nu suffix p plus q greater than or equal to by the triangle function tau of nu suffix p comma nu suffix q. And the next condition should satisfy is you take any alpha from closed interval 0, 1, nu suffix p should be less than or equal to tau star of nu suffix alpha p and nu suffix 1 minus alpha into p. So if these four conditions are satisfying for the mapping nu, then we are calling the mapping nu as the probabilistic norm on this linear space V. And if you take this triangle function tau as our that supremum definition initially told, some of the typical continuous triangle functions I have told earlier. If you take tau equal to tau suffix t and tau star is that infimum one, then the quadruple in V nu tau suffix t, tau suffix tau star, which we are denoting by a quadruple that is V nu t, it is called the Menger probabilistic norm space. It's a different version of probabilistic norm space. So this is a somewhat a broad one. We can tell that this will be a particular class of the general probabilistic norm space. So in this probabilistic norm space, you just take the N1 condition and N3 condition. Together with that N1 condition, nu suffix p is equal to epsilon naught if and only if p equal to the null vector in the vector space, and somewhat similar to this triangle inequality type. Together with one additional condition, this is somewhat similar to our scaling property in our usual normed vector space. That is nu suffix alpha p of x is equal to nu suffix p of x by mod alpha. Then such spaces are called Stirner space. A probabilistic norm space is said to be a Stirner space if together with the first and third condition, if this additional condition comes, then we can tell that it's a Stirner space. So I will show some 2 to 3 examples here without illustration. You take any norm space V with a norm, define a new suffix p as epsilon suffix norm p, and you take a triangle function tau with a condition that tau of epsilon a epsilon b is equal to epsilon suffix a plus b for all a and b greater than 0, and take a triangle function tau star with the condition that tau is this defined tau is less than or equal to tau star. For example, you can take tau equal to tau suffix t and tau star equal to tau suffix tau star for all continuous t norms t and t connorm t star. Then you can see that V nu tau star is a Pn space. It will satisfy all the conditions of probabilistic norm. To take a next example, for that again I am considering a real normed space. From a real normed space, I am defining a mapping nu from V to delta plus, defined by nu suffix p of t for all t belongs to open interval 0 infinite, t divided by t plus norm t, and at t equal to infinite I am defining it as 1. Then how can we take the triangle functions? I am taking the tau as pi suffix pi. How that pi suffix pi is defined? Pi suffix pi of f comma g at t is defined as f at t into g at t. And pi suffix pi star, that is our tau star. It is defined as what? F pi suffix pi star of fg at t is f of t plus g of t minus f of t into g of t. That means this is a t norm and this is the corresponding t connorm. Then one can verify all the conditions of that probabilistic norm. So this quadruple is a probabilistic norm, and this is called the canonical probabilistic norm associated with any normed space. This is the way we can construct a probabilistic norm from a normed space. So the next example, you take the vector space as set of all real numbers and tau as tau suffix w, and it's called t connorm as tau suffix m. Then define the map nu from R to delta plus nu at p equal to 0, that nu suffix 0 I am fixing as what? Epsilon 0. And for all p not equal to 0, nu suffix p of t, which is nothing but 1 by norm p plus 2 into epsilon 0 of t plus this term. I am not reading that one. You can see that definition there. So with respect to the given norms, one can see that this quadruple is a Pn space. So the next thing is how to define a topology on Pn space. So normally in the classical norm space, we have seen, and yesterday Vinod sir also told that from a norm space, we can construct a metric. So similarly, the question arises here is how to construct a probabilistic metric from a probabilistic norm space. So I am taking a probabilistic norm space here V. Then if I define a map f from v cross p to delta plus by f of p is equal to nu suffix p minus q, then this definition we can verify all the conditions of probabilistic metric, and
then we can tell that V together with this F and the corresponding triangle function tau becomes a probabilistic metric space. That means you can tell that every probabilistic norm space is a probabilistic metric space. So I'm taking the neighborhood systems here, that is NP of T is equal to set of all Q in V such that nu suffix Q minus P of T is greater than 1 minus T. Or in other words, we can tell, this is already I told in earlier slide, with respect to the Sibley metric, how can we tell set of all Q in V such that the Sibley metric between V, Q minus P and epsilon naught should be less than T. And this determines a topology on V on the probabilistic norm space. That topology is called the strong topology here. So this fact we can establish through a following theorem. It's a proved result. If you take any Pn space with a continuous triangle function tau, then the strong neighborhood system capital N, then what is the strong neighborhood system capital N is union of this one. So it determines a Hausdorff topology for this probabilistic norm space. So this is the way we are constructing what a topology on a Pn space. So next I want to talk about what do you mean by strongly convergence and strong Cauchy sequence in probabilistic norm space. If you take a sequence Pn from the probabilistic norm space V, it is said to be strongly convergent to P in V if for each lambda greater than 0, there exists a positive integer m such that after that stage m, what should happen? It should be nu suffix Pn. Nu suffix Pn should be in what? Np of lambda. So how can we tell a sequence is said to be a strong Cauchy sequence in probabilistic norm space corresponding to any lambda greater than 0 after the stage capital N? Nu suffix Pn minus Pm of lambda should be greater than what? 1 minus lambda. Otherwise, in terms of Sibley metric, we can tell that distance between nu suffix Pn minus Pm with epsilon naught should be less than lambda. So in this strong topology, constructed using this neighborhood system, the closure of NP of lambda is defined as NP of lambda union NP of lambda dash, lambda prime. So NP of lambda prime is nothing but the set of all limit points of all convergence sequence in the NP of lambda. And you can see that the strong topology is first countable and Hausdorff. So the complete metric space can be completely specified in terms of what? Strong convergence of sequences. So the next question comes is when this probabilistic norm is uniformly continuous. And in the classical norm space, we know that uniformly continuous mapping is a mapping from V into R, and it is proved as an immediate consequence of what? Our triangle inequality. But in that same line, we cannot establish in probabilistic norm space. To establish the uniform continuity of the probabilistic norm, we need one lemma. The lemma says that if you take a continuous triangle function and S be the set of all triples from delta plus Cartesian product with what? Delta plus Cartesian product with delta plus, that is delta plus power 3. You take triplet FGH such that F is greater than or equal to tau of Hg and G is greater than or equal to tau of Hg, then for all eta greater than 0, there exists a positive number delta such that Corresponding to FGH, distance symmetric between H and epsilon naught less than delta implies symmetric between F and G should be less than eta. If that condition holds, then only we can establish the result for what? The uniform continuity of a probabilistic norm. It says that if V is a probabilistic norm space with a continuous triangle function tau, and V is endowed with strong topology defined on delta plus, strong topology and delta plus with the topology of symmetric, then the probabilistic norm nu is uniformly continuous. So in that proof, we are using this previous lemma to establish that this probabilistic norm is uniformly continuous. So next, once we have a structure of probabilistic norm space, one of the major question arises in that context is, can we make a probabilistic norm to a topological vector space? You know that what do you mean by topological vector space? Topological vector space means what? It's a vector space in which the operations, underlying operations should be continuous. So here the question is, for the probabilistic norm space to be a topological vector space, the sum defined on V, that is PQ is going to P plus Q, and for all alpha in R, the mapping P going to alpha P, and the next one, alpha going to alpha P must be continuous. Generally in the topological vector space, we are seeing only this continuity and this continuity, that is addition of vectors and scalar multiplication. Here, to establish that one, we need to get rid of these three. So for that one, we need some of the results to check whether it is a topological vector space or not. So if you take a Pn space V, in that V together with its strong topology and delta plus with its topology from the symmetric, and V cross V is corresponding to the product topology, then the addition defined on V is uniformly continuous map from V cross V to V, so that one can conclude that the structure V together with that addition is a topological group. So the next result which established that if you take a Pn space with a continuous continuous triangle function tau, and with the same setting V with the strong topology and delta plus with the topology formed by the symmetric, then the mapping S from V cross V to delta plus defined by S of PQ, which is defined as nu suffix P plus Q, is a uniformly continuous mapping. So we need some 2 to 3 lemmas to establish the continuity of those operations involved in V. So next, in order to prove the continuity of mapping P to P going to alpha P, we need the next lemma. The next lemma says that in a Pn space, if you take any two real numbers alpha and B, with the condition that alpha less than or equal to B and both are positive, then nu suffix beta times P will be less than or equal to nu times alpha times suffix P for all P in V. And this next lemma, you can see that one. For any real number alpha and any element from the Pn space, and for every eta greater than 0, there is a delta such that if the symmetric between nu P and epsilon naught is less than delta, then the symmetric between nu suffix alpha p and epsilon naught will be less than eta. So I am just listing these lemmas because without listing these lemmas, it is not meaningful to tell the next result. So with these three lemmas, we can prove that for every real number alpha, the mapping P going to alpha P is uniformly continuous on V. So now the third mapping arises. In general, we can tell that alpha going to alpha P in a probabilistic norm space is not continuous. That we can establish by the following example. If you take the real vector space with the triangle function as tau w and its conorm as tau suffix m, then define a probabilistic norm nu in a way that nu suffix p nu 0 is equal to epsilon naught, and for all p not equal to 0, this nu p. You can see that it's a probabilistic norm space, but for every non-zero p and for every sequence alpha n which tends to 0, if you take the sequence nu suffix alpha and p, which will converge weakly to the point epsilon naught plus epsilon infinite by 2, actually it should go to epsilon naught, then only we can tell that it is continuous. Since it is going to epsilon naught plus epsilon infinite by 2, so we can tell that this mapping is not continuous. So we got that this mapping is not continuous in general. That means which established that every Pn space is not a topological vector spaces in general. That means first two mappings we got it as continuous, but this third one is not coming out to be continuous. So the question arises here is, can you make it as a continuous one? So we can make it as a continuous one. Based on the next lemma, we can come to a conclusion. The next lemma will give a sufficient condition. The lemma says that if the triangle function tau star is Archimedean, then for every p belongs to V such that nu p different from epsilon infinite, and for every eta greater than 0, there exists a delta greater than 0 such that this condition holds. This condition holds means as alpha tends to infinite, the Sibley metric between nu alpha p and epsilon naught equal to 0, then that previous mapping will be continuous. That means the underlying assumption should be to make a Pn space to be a topological vector space is the corresponding tau star should be Archimedean. That means the sufficient condition that ensures that the mapping alpha to alpha p continuous is tau star is Archimedean. So with the help of that one, it is proved that every Pn space with this tau star is Archimedean, then this mapping is continuous. So with the help of all these previous results, one can conclude that every Pn space with a triangle function tau star is Archimedean is a topological vector space. That means all Pn spaces are not topological vector spaces only if tau star is Archimedean. So this result is established through an example also. If you take a normed space and if you set up the triangle function tau in this way and the norm p defined in this particular form, then one can easily see that the quadrupole is a Pn space as well as a topological vector space. So next question is, what about the completeness of a probabilistic norm space? The completeness of probabilistic metric space was studied in 1966 and 71 period, and they have proved that every probabilistic metric space admits completion. Then the natural question arises, what about in probabilistic normed spaces? So it was answered in 1995 by Laforza-Gullien and Sempi. They proved that it is true for the completeness exists for search norm space as well as probabilistic norm space. I will just state here that one. Every probabilistic norm space with a continuous triangle function tau has a completion. That means it is isometric to what? A dense linear subspace of a complete Pn space. And this completion is unique up to isometries. So next is, what about finite dimensional Pn spaces? Any particular result is existing in finite dimensional Pn spaces. Every finite dimensional subspace of a Pn space together with a triangle function tau star is Archimedean is complete. It's a well-known result proved in the finite dimensional Pn spaces. That means in particular we can tell that every finite dimensional Pn space is complete. So how can we define the equivalence of two norms? The equivalence of two norms can be defined such that for every sequence, if you take Pm in V, then Pm converges to P with respect to the first norm nu, if and only if Pm converges to P with respect to the second norm. So that way we are talking about the equivalence of two norms. So we are getting a condition for a finite dimensional Pn space. Every probabilistic norms nu and mu are equivalent whenever the tau star and the tau dash star, that is whenever the t conorm of the triangle function tau and the t conorm of the triangle function t dash are Archimedean, then we can tell that they are probabilistic. Those two probabilistic norms are equivalent. So with this one, I am planning to wind up. I want to tell that some of the recent developments happened in probabilistic norm space. One can study about the normability of Pn space. That means, can you find out a norm on that probabilistic norm space such that which generates a topology? And recently in 2018, some of the Iranian researchers had established some of the well-known theorem in our classical norm space. There is open mapping theorem, closed graph theorem, uniform boundedness principle, and Banach-Steinhaus theorem in Pn spaces that indicates that there are many results in our classical Banach spaces to our Pn spaces yet to be established. So with this presentation, I am not telling that everyone will understand these concepts in detail. At least some students can take up this as a step into this area and think to do some small project during your MSc program and try to study this concept and try to give some contribution to this area. So with this one, I would like to stop this presentation. And I want to show some of the references. Those who are interested, you can see the concepts of probabilistic metric spaces can be get from this textbook, but it is not available online. But in some of the premier institutes like ISI and all, it is there. I have got a copy from there. And till whatever the works done till 2014, it has been included in this textbook, probabilistic non-space, and I got an opportunity to be a part of that books also. And some of the recent developments in this normability results in this Pn spaces is published in this paper. And this is that book I have told. Okay, thank you.
Then thank you, Harikrishna sir.
Thank you.
Any questions from audio? Any questions from audience?
It is slightly difficult to ask some questions because this area is very new to all people.
Okay, sir.
Because
Okay.
that's why I want to give some of the recent research lines to the MSc students. Some people will be interested to do some projects or something in this one. That's why I have taken this topic.
Okay, sir. Now I invite Ms. Anjana, second year MSc students, to propose vote of thanks.
Hello, good morning. Hello, Miss.
Good morning. It's all.
On behalf of Malabar Christian College and the entire fraternity of the institution, first of all, I extend my most sincere thanks to Dr. P.K. Harikrishnan sir for conducting such a wonderful session. A big thank you for giving an excellent coverage to the topic, Introduction to Probabilistic Norm Spaces and some related concepts. I also wish to express my gratitude to our principal, Dr. D.P. Godwin Samraj sir, our HOD, Sindhu Miss, the program coordinator, Shyama Miss, Associate Professor, Dr. P.C. Pradip sir, and IQAC coordinator, Dr. Srijit sir, for your enormous cooperation in the organization of the seminar. Sir, this was really a wonderful session, and your presentation was excellent. You presented the topics in a simple manner so that we were able to go deeper to these topics without any difficulties. So I am sure that this session will be very helpful for everyone of us who participated in this seminar. So once again, thank you everyone for giving us an opportunity to attend the seminar. Thank you.
Thank you, Anjana. Question. Addiction, sir?
Yes.
Question in comment box.
What are the loopholes of functional analysis filled by probabilistic norm schools? So I'm not clear about that question. What that Akash Chain mean with that one? What are the loopholes of functional analysis filled by probabilistic norm spaces? No, actually, probabilistic norm space is not fulfilling any of the concepts or any of the gaps in the functional analysis. It is entirely a new structure. Probabilistic norm space is entirely a new structure. What we are trying to do is in that new normed structure, what way we can translate the existing concepts in the classical functional analysis to that area. Some of the concepts won't directly work in that probabilistic norm spaces. So then under what condition we can make it? For example, I have told that probabilistic norm space is not a topological vector spaces in general. So then we have thought for under what condition it can happen. So when the triangle function will become Archimedean, in that case we can tell that probabilistic norm space can be what a topological vector spaces. Like that, we have to see the theory one by one. The probabilistic norm space is not completely done. Probabilistic functional analysis still going on. Many of the classical results are developing and finding out. That is why I told that those who are interested in that area, you can start working on that one. If you are able to establish some of the results in that one, that is your own result. Okay, thank you.
Thank you, sir. Dear participants, e-certificates will be provided to all the participants by submitting the feedback form. I sent the feedback form in Telegram, also in your mail. Thank you, one and all.
Thank you, Shama and Sindhu ma'am.
Sindhu ma'am, can you wind up?
Yes, we can wind up. Then the recorded video will upload on Monday through YouTube, and the link will be provided in in the Telegram channel, and also your mail. Here is some net problem. So Monday we will upload.
Dear participants, please wait some time after submitting the feedback to get your certificates, and do not post multiple feedbacks. Okay, thank you. Thank you, one and all.
Thank you, Hari Krishna, sir. Thank you very much.
Thank you, madam.
Okay, sir.
Okay, thank you.